Section: Introduction. In this section, we discuss how recent advancements in language models, LLMs, have greatly changed natural language processing, enabling the generation of high-quality artificial text. These models have made information more accessible and are now vital for various applications, including automated communication and solving math and programming problems. However, their rapid development and widespread use also bring risks to social, political, and economic systems. The ability of LLMs to create text that resembles human writing raises concerns about misuse, such as academic cheating, misinformation campaigns on social media, and threats to democratic processes. To tackle these issues, researchers have focused on watermarking LLMs, which involves embedding a signal in the generated text to identify whether it was produced by a machine. For watermarking to be effective, it needs to meet several criteria. It should be easily detectable with statistical guarantees. It should not compromise the quality or speed of the generated text, and it should remain detectable even after common types of text corruption. Among these criteria, having formal statistical guarantees is crucial, especially in sensitive situations like accusations of cheating, where unreliable detection can lead to serious consequences. Previous research has established rigorous statistical guarantees for watermarking by embedding patterns into the text generation process. These methods often prioritize making the watermarked text look very similar to unwatermarked text, but this can ignore the natural structure of language and may affect other important properties like robustness and efficiency. We note that strict similarity is not always necessary, as humans often struggle to distinguish between high-quality generated text and slight variations. Recent findings suggest that using less stringent measures, like maximum mean discrepancy, could be sufficient for our purposes. Additionally, language has complex structures that modern models learn and incorporate. In our work, we introduce a new approach called 2-number-2, which leverages the inherent structure of text by adjusting model weights during generation and testing for statistical independence during detection. This method is based on observations that language models can handle small weight changes without losing output quality. Our approach is straightforward to implement and efficient, ensuring strong detection capabilities without sacrificing model performance. We provide theoretical backing for 2-number-2, showing it offers a valid statistical test and reasonable detection power under natural assumptions. Through extensive experiments, we demonstrate that 2-number-2 is highly detectable, maintains the quality of generated text, and shows some resilience to both token-level and semantic corruption. We summarize our contributions as follows. We introduce 2-number-2 as a practical and efficient watermarking scheme with no impact on generation speed. We explain the motivation behind 2-number-2 using classical statistical theory and provide rigorous guarantees on its statistical validity. Our experiments showcase its detectability, quality retention, and robustness. In the appendices, we include details on various experiments, parameter effects, and examples of watermarked text generated by 2-number-2. We also suggest a modification to further reduce the watermark's impact on quality while maintaining detectability and explore its effects in our additional results. Lastly, we compare 2-number-2 to other schemes, highlighting its advantages in quality and generation speed despite being slightly less detectable. Section Summary. In this section, we discuss the transformative impact of recent advancements in language models, LLMs, on natural language processing, highlighting both their capabilities and the associated risks, such as misuse in academic and social contexts. We introduce our novel watermarking approach, 2-number-2, which leverages the inherent structure of language to ensure effective detection without compromising text quality or generation speed, while also providing rigorous statistical guarantees. Section: Problem Setup and Prerequisites. In this section, we formally define the watermarking problem using the principles of statistical hypothesis testing. We begin by explaining the basics of hypothesis testing and introducing the necessary notation. Next, we provide definitions relevant to language models. Finally, we frame the issue of watermarking text produced by language models as a specific case of hypothesis testing, which will be the basis for the rest of our paper. In hypothesis testing, we recall the standard framework from classical statistics. We have a domain and two hypotheses: the null hypothesis, which is a collection of probability measures, and the alternative hypothesis. If either hypothesis consists of a single measure, we call it simple. Otherwise, it is composite. A test is any measurable function. We assume there is a true distribution, and given a sample, we use the test to determine whether we can confidently assert one hypothesis over the other. There are two types of errors to consider: type 1 error, which is the false rejection of the null hypothesis, and type 2 error, which is the false acceptance of the null hypothesis. We control these errors through the test's level and power. The level of a test indicates the maximum probability of incorrectly classifying a sample from the null hypothesis as coming from the alternative hypothesis. The power of a test reflects the probability of incorrectly accepting the null hypothesis when the true distribution is from the alternative hypothesis. A p-value is a function that measures the evidence against the null hypothesis, representing the probability of observing a result as extreme as the one we have, assuming the null hypothesis is true. Smaller p-values suggest that the null hypothesis is less likely. We aim to create tests that minimize the chance of rejecting the null hypothesis when it is true while maximizing the chance of rejecting it when the alternative hypothesis is true. We formalize the watermarking problem as a hypothesis testing scenario where we develop a statistical test to differentiate between the hypothesis that a text is generated by a specific watermarked model and the null hypothesis that it is not. Next, we introduce language models. A language model, defined by its parameters and token space, is a function that maps a sequence of previous tokens to a distribution over the next token. Given a prompt and a specified length for text generation, the model produces text by sampling from this distribution. For simplicity, we often represent this sampling process in a condensed form. We then formalize watermarking as a hypothesis testing problem, a method that has been used in previous studies on watermarking language models. This approach provides strong statistical guarantees for detection, which are vital in practical applications like plagiarism detection. A watermarking scheme consists of two procedures. Given a prompt space, a key space, and a sample space, watermarking occurs in two steps. The first procedure, parameterized by a language model and a distribution, samples a key and generates watermark text based on the prompt. The second procedure tests statistical hypotheses using the watermarking key and candidate text. Our goal in designing an effective watermarking scheme is to select a key such that the modified language model produces text that is distinct from the original model when the key is known, while still maintaining good quality and being hard to distinguish when the key is unknown. We ensure that the null hypothesis does not assume a specific distribution for responses, allowing for the inclusion of text generated by humans or other models. This formulation is similar to previous work, but we do not impose the additional requirement of closeness in distribution, as we believe that standard metrics for quality degradation are sufficient. Section Summary. In this section, we define the watermarking problem using statistical hypothesis testing, introducing key concepts such as null and alternative hypotheses, and the role of p-values. We formalize watermarking as a hypothesis testing problem, aiming to create a scheme that distinguishes between text generated by a watermarked language model and other texts while maintaining high quality and utility. Section: Additional Notation. In this section, we introduce additional notation that will help clarify our work. We denote a set of elements with specific symbols, where a vector's norms are represented in a straightforward manner. The identity matrix is indicated for a particular dimension, and we define a set of distributions over a given set. We also represent an isotropic Gaussian distribution with a specified variance. The concatenation of token strings is denoted by a specific symbol, and we indicate the product of two distributions, assuming the samples are independent. Next, we present our novel watermarking scheme, which consists of two main components, a generation procedure and a detection procedure. After detailing our scheme, we will provide motivation for our approach and formal theoretical guarantees regarding the effectiveness of our detection test. Our watermarking scheme can be applied to any parameterized model, where we sample a watermarking key from a centered multivariate Gaussian distribution with a small covariance value. We then create the watermarked model by slightly altering the original parameters using this key. When given an input prompt, we generate a watermarked response by sampling from the modified model. In the detection procedure, we test a composite hypothesis regarding the independence of two elements against an alternative hypothesis. We use a specific test statistic and reject the null hypothesis if a certain condition is met, which indicates that the text is watermarked. It is crucial that our test remains valid for the composite null hypothesis, allowing for variations without strict assumptions about the distribution of the text. We chose a Gaussian distribution for our watermarking key because of its desirable properties, such as rotational invariance and independent directions. While we could use other distributions with similar characteristics, the Gaussian serves our purpose well. To illustrate how our scheme works, we consider a scenario where the watermarking key is independent of the text under the null hypothesis. This independence allows us to derive certain relationships which differ under the alternative hypothesis. We apply standard statistical methods to analyze the power of our test, noting that higher dimensions improve its effectiveness. In terms of practical implementation, we recognize that modern language models have billions of parameters. However, we find that effective watermarking can be achieved by modifying just one weight matrix in a single layer. This method minimizes any potential negative impact on model quality, as we can achieve statistical distinguishability without degrading performance. Moreover, our detection method requires minimal memory overhead, as it only involves a single forward pass through the model and a backward pass through the modified parameter. This approach is efficient and integrates seamlessly into existing generation pipelines, imposing no additional computational cost compared to unwatermarked models. We will now discuss the motivation behind our approach and present formal results regarding its effectiveness. Section Summary. In this section, we introduce our novel watermarking scheme for language models, which consists of two main components: a generation procedure that creates a watermarking key using a multivariate Gaussian distribution, and a detection procedure that tests for the presence of the watermark. We emphasize that our approach is practical, requiring minimal modifications to the model and maintaining inference efficiency while ensuring statistical validity in detecting watermarked outputs. Section: Motivation. In this section, we discuss the motivation behind our approach. We recall that in hypothesis testing, we aim to manage two types of errors: false positives, which we control through the test's level, and false negatives, which we manage through the test's power. These two goals often conflict, leading statisticians to seek tests that maximize power while adhering to a level constraint, or to control the risk associated with the test. When the null hypothesis is convex, we find that the optimal test can be represented as a likelihood ratio test against the worst-case distribution under the null hypothesis. This means we identify a specific distribution that, when compared to a threshold, maintains the desired level of the test. However, determining this worst-case distribution can be challenging, especially in our context, where it is unclear how to characterize it or compute necessary values. To address this, we shift our focus from total variation to Kullback-Leibler divergence. We find that the closest distribution in our context can be derived by marginalizing over certain measures. If we have a composite hypothesis and a simple alternative, we can express the projection of the alternative onto the null hypothesis in terms of Kullback-Leibler divergence. We propose that a reasonable strategy for our optimal test is to reject the null hypothesis when the log likelihood ratio is sufficiently large. However, calculating the threshold for this test can be complex. To simplify, we approximate the log likelihood test and focus on a specific case, allowing us to ignore certain scaling terms. By applying a first-order Taylor approximation and leveraging properties of Gaussian distributions, we can derive a test statistic that is computationally feasible and retains power similar to the original test. We also note that due to the properties of Gaussian distributions, we can easily determine the threshold from the cumulative distribution function. Next, we formalize our findings by establishing bounds on the statistical validity and power of our test. We assume that the mapping we use is differentiable. Our first theoretical result provides a bound on the level of our test, confirming that it maintains the desired level and produces valid p-values. This ensures that our procedure effectively controls the false positive rate, which is crucial for applications like watermarking. Finally, we outline a scenario where we can reliably bound the power of our test, further solidifying its effectiveness. Section Summary. In this section, we discuss the challenges of controlling false positives and false negatives in hypothesis testing, highlighting that the optimal test often involves a likelihood ratio approach. We establish that our proposed test maintains statistical validity and controls the false positive rate while also providing a framework to bound its power. Section: Linear Softmax Model. In this section, we discuss the linear softmax model. While we can ensure statistical validity without conditions, we need to make certain assumptions about the model to achieve meaningful power. For instance, if the model parameters are constant, we cannot expect to detect any watermarking since all models would be the same. To address this, we focus on parameterized models relevant to language models, LLMs. We define a linear softmax model using discrete spaces and model parameters, along with a known feature map. For any given input, if the conditional probability follows a linear softmax model, then the overall model does as well. We use this model to approximate LMs and assess the power of our test, noting that this approximation aligns with autoregressive generation. In practice, we apply watermarking by introducing noise to a feed-forward layer within a transformer block. By fixing other model parameters and only adjusting those where we add noise, we find that the conditional distribution for predicting the next token behaves like a nonlinear softmax model. We assume that this nonlinear function behaves well near the trained model's parameters, allowing us to approximate it linearly. Our findings suggest that modern transformers can be treated as approximately linear softmax models, especially in small neighborhoods around their trained parameters. Empirical evidence from model merging supports this linear behavior. However, we note that as the parameter size increases, the power of our test diminishes. We establish bounds on the power of our test under the linear softmax model. If our model is defined by a linear softmax structure, we can determine the level and power of our hypothesis test. The multiplicative factor in our calculations adjusts the underlying distribution to favor certain outcomes, which generally increases the test's power when we focus on those outcomes. We also recognize that if the responses vary significantly, the optimal responses for maximizing different aspects may not align, complicating our analysis. To simplify our understanding, we consider a scenario where certain conditions hold, leading us to conclude that the power of our test is influenced by the distribution of specific variables. In ideal conditions, we expect our test to achieve a certain power level, indicating that larger models are easier to watermark. We observe that the condition number affects the effective dimension of the model, which in turn impacts the test's power. Our empirical observations suggest that larger noise levels and longer sequences facilitate watermarking. We further quantify the conditions under which our idealized setting holds, establishing that if certain assumptions are met, our test maintains a specific power level. Additionally, we extend our analysis to include cases where the distribution is strongly log-concave, demonstrating robustness against various modifications. Finally, we highlight that our primary detection method shows resilience against different types of alterations, and we provide a theoretical analysis of a variant of our test that enhances its robustness against random token-level corruptions. Section Summary. In this section, we explore the linear softmax model to analyze watermarking detection in language models, emphasizing that while statistical validity is guaranteed, non-trivial power requires specific model assumptions. We demonstrate that modern transformers can be approximated as linear softmax models in small parameter neighborhoods, which enhances our understanding of the test's power and its dependence on model complexity and noise levels. Section: Experiments. In this section, we empirically validate our watermarking scheme. Unlike previous works that focus on watermarks that are undetectable or cause no distortion, our approach depends on a noticeable statistical difference between watermarked and unwatermarked text. Therefore, it is crucial for us to assess the quality of our watermarked models to ensure that our method does not significantly degrade the quality of the generated text. We will outline several key experimental details, with a complete description of our setup available in the appendix. We first evaluate the detectability of our method, referred to as 2 number 2, and then examine its impact on model quality. We also explore how robust 2 number 2 is against various types of corruptions. Lastly, we investigate a modified version of 2 number 2 that allows for less impact on model quality compared to the standard version. For our experiments, we utilize the Hugging Face repository to load our models, VLLM for text generation, and PyTorch for watermark detection. To assess the quality of our watermarked models, we employ Eleuther's LM evaluation harness and the Alpaca eval framework. All experiments are conducted on 40 GB NVIDIA A100 GPUs, ensuring that each model is small enough to run on a single GPU for both generation and detection. Regarding key experimental details, the 2 number 2 procedure can be used with minimal adjustments, requiring careful selection of two main hyperparameters: the variance of the Gaussian noise and a specific parameter configuration. It is important to note that the statistical validity of our approach is independent of these parameters, while the effectiveness of our method largely depends on a sound linear approximation. Choosing these hyperparameters requires careful consideration to ensure that the distribution of watermarked text is distinct enough for detection, without negatively affecting the quality of the generated text. Thus, selecting these parameters is a delicate balancing act. For each language model we consider, we set the specific parameter configuration to a single MLP layer. We ensure that the evaluation metrics of the model remain comparable to those of the unwatermarked version, and we refine the hyperparameters to conduct a robust test. To assess whether 2 number 2 can be detected, we use the real news-like split of the C4 dataset as prompts for generating watermarked text. We apply the same 1,000 prompts across all models and watermarking keys to maintain fairness in comparison. We focus on 3 recent language models: 6 number 6, 7 number 7, and 5 number 5. Notably, versions of 6 number 6 and 7 number 7 have been used in previous watermarking studies as benchmarks. In contrast, 5 number 5 has been instruction fine-tuned, resulting in better performance on reasoning, math, and coding tasks, as well as generating lower entropy sequences. Previous research has shown that lower entropy sequences are more challenging to watermark, which is reflected in our theoretical framework. We find that 5 number 5 presents a particular challenge for watermarking, as evidenced by our empirical results. As we generate more tokens, we observe an increase in the expected squared norm of the gradient, which correlates with the median p-value for each model. This relationship aligns with our theoretical predictions. A key advantage of 2 number 2 is its speed in both generation and detection. Generating 1,000 tokens takes only milliseconds, while detection requires less than a second for the same number of tokens. When we compare these times to other methods, we find that our approach is significantly faster and has lower latency. Additionally, 2 number 2 can be easily integrated into various generation accelerators, unlike alternative methods that often require custom implementations. Due to space limitations, we will provide further investigation and detailed analyses of how different parameters affect detectability in the appendix. Section Summary. In this section, we empirically validate our watermarking scheme, focusing on the detectability and quality of watermarked text while ensuring minimal degradation in model performance. We detail our experimental setup, including the selection of hyperparameters and the use of various language models, demonstrating that our method is both fast and effective in generating and detecting watermarked content. Section. In this section, we explore whether our watermarking method, referred to as 2 number 2, affects model quality and its robustness. A key aspect of a watermarking scheme is its ability to withstand alterations, whether these changes are made intentionally, like avoiding plagiarism, or unintentionally, such as when only part of a model's output is used in a final document. For our watermark to be effective, it must be resilient to these modifications. We examine 4 common types of corruptions discussed in the literature: 3 token-level corruptions, random insertions, deletions, and substitutions, and a more complex paraphrasing attack known as round-trip translation, where the text is translated to another language and back to English. We provide details on how these attacks are implemented in our appendix. Our findings show that the ability to detect watermarked text decreases as more of it is corrupted, with the robustness varying significantly based on the model and type of corruption. Notably, our method retains considerable detection power even when half of the tokens are corrupted. However, we acknowledge that these token-level attacks are somewhat simplistic and do not accurately represent real-world threats, as the quality of the corrupted text is significantly lower. To address this, we present ROC curves for each model after round-trip translation through French. Despite the increased difficulty, all models still show meaningful detection capabilities, indicating some level of robustness in this more realistic scenario. We also note that our watermarking method requires knowledge of the prompt, as the detection process relies on understanding the generated tokens based on the input. Since this knowledge is often unavailable, we investigate how inserting, deleting, or substituting tokens at the start of the input affects detectability. We find that our method is quite robust even without prompt knowledge, with the stability of detection remaining relatively high across various prompt alterations. Next, we consider whether we can enhance number 2 through rank reduction. We recognize that a major challenge is selecting the right parameters to add noise while balancing detectability and model quality. Previous research indicates that the highest principal components of language model weight matrices are crucial for predictions, while lower components can be seen as noise. This leads us to propose a rank-reduced version of number 2, where we focus on the subspace formed by the lower principal components. Our results show that this rank-reduced approach allows us to add more noise without degrading model quality. We observe similar detection trends as in the original number 2 across various response lengths. Additionally, by further reducing the rank of the watermarking space, we can tolerate greater variance without impacting model performance. However, we also find that the rank-reduced watermarks are less robust to corruption compared to the original number 2. Whether this is a fundamental characteristic of the rank reduction method or a consequence of our chosen parameters remains a question for future investigation. Section Summary. In this section, we examine the robustness of our watermarking scheme against various types of text corruption, finding that while it retains significant detection power even under challenging conditions like round-trip translation, the robustness varies by model and corruption type. We also propose a rank-reduced version of our watermarking method that allows for greater noise addition without degrading model quality, although it appears to be less robust to corruption compared to the original method. Section: Related Works. In this section, we discuss the most relevant works on watermarking large language models, LLMs, and direct readers to other sources for a comprehensive overview of watermarking methods for text, images, and audio generation. We categorize watermarking approaches with statistical guarantees into 2 main types: distortionary and non-distortionary. Distortionary schemes change the distribution of the model's next token predictions. For instance, some methods divide the vocabulary into a red set and a green set, favoring the green set in a way that can be detected by analyzing the frequency of tokens in the generated text. While these methods provide theoretical guarantees, they often distort the generated text significantly and are susceptible to paraphrasing attacks. We compare our approach to another scheme empirically. On the other hand, non-distortionary schemes hide the watermark by affecting the pseudo-random number generator used for sampling tokens. Although there are robust examples of this type, they struggle with scalability because the watermarking key must be as long as the number of queries to the model, leading to impractically large keys and slow detection times. To address these limitations, some researchers propose stronger, cryptographically inspired undetectable watermarking schemes that use a hash function based on a secret key. However, these schemes are not yet suitable for large-scale use in LLM generation due to increased generation times. For example, One scheme takes hundreds of seconds to generate and detect, while our method achieves much faster speeds. Our approach is white box, meaning it requires access to the model's weights and is distortionary. However, we show that the changes we make do not significantly affect the model's quality. While the aforementioned schemes offer strong theoretical foundations, they have not been thoroughly tested in practice, except for a few. To overcome the limitations of these methods, SynthID text was proposed, which implements ideas similar to previous approaches. Although it works efficiently on certain models, it lacks statistical validity in its empirical evaluations. Their method involves training a detector to classify watermarked and unwatermarked text, but this approach may not be robust against out-of-distribution prompts or responses from different models or humans, making it unreliable for practical use. An alternative to creating rigorous watermarking schemes is to develop algorithms that can later determine if a text is likely AI-generated or human-written. This can be done by analyzing the statistical properties of the text or using trained classifiers. However, as language models improve, distinguishing between AI and human text will become increasingly challenging. For applications like detecting cheating in educational settings, a well-calibrated method with formal statistical guarantees is crucial. Lastly, we note that some earlier works have explored altering model weights to prevent intellectual property theft. While our method also modifies the model's weights, our goal is to watermark the generated text rather than the model itself. Section Summary. In this section, we review relevant works on LLM watermarking, categorizing approaches into distortionary and non-distortionary schemes, each with distinct advantages and limitations regarding statistical guarantees and practical deployment. We also discuss alternative methods for post-hoc detection of AI-generated text and highlight our approach, which focuses on watermarking generated text through weight perturbation while maintaining model quality. Section: Attacks on watermarked models. In this section, we discuss the challenges faced by watermarking models. Several studies have shown that well-resourced adversaries can undermine watermarking techniques. They can learn these schemes using a student-teacher approach and have developed further attacks that are often resource-heavy, requiring repeated access to systems that can generate high-quality text variations or assess text quality. With enough resources, an adversary can completely bypass these schemes by training their own unwatermarked AI model. We introduced a new watermarking scheme, called 2-number-2, which offers theoretical assurances of statistical validity and effectiveness. Through extensive testing, we showed that 2-number-2 is straightforward, easily detectable, and does not significantly affect model performance or generation speed. We will now outline the pros and cons of 2-number-2 compared to previous watermarking methods and suggest future research directions. The main advantage of 2-number-2 is that it is the first simple and efficient watermarking scheme that can be seamlessly integrated into existing systems without any modifications or delays in generation speed. Additionally, it has a very fast detection speed and similar memory requirements to those of inference. 2-number-2 is also quite resilient to corruption and can detect watermarks without needing to know the prompt or any specific details about the text. Unlike many other schemes that focus on the next token sampling process and are limited to certain types of corruptions, 2-number-2 alters the text distribution itself, making it more robust against various corruptions like paraphrasing and translation. However, 2-number-2 has some limitations. First, it lacks formal guarantees of distortion-free or indistinguishable outputs, and while we have shown it does not significantly degrade model quality across various benchmarks, more research is needed before it can be safely used in real-world applications. Second, 2-number-2 generally requires more tokens to reliably detect a watermark compared to some alternatives, but its speed allows it to remain competitive. Third, it requires white box access to model weights for detection, which we see as reasonable since it assumes the language model provider offers watermark detection as a service. Lastly, 2-number-2 is somewhat less robust against edit-level corruptions compared to some other methods, although it may be more resilient than certain implementations that prioritize text quality. Looking ahead, we see 2-number-2 as a step toward creating structural watermarks in language models, but the best approach for this is still uncertain. We suggested adding noise to low-rank components of the model weights to balance model quality and watermark detectability, but we did not explore other potential methods. These could include training the model after adding noise, targeting specific subnetworks based on their relevance to performance, and other strategies. We also did not investigate the possibility of combining different watermarks, which might enhance robustness at the expense of increased detectable noise.